Welcome! Today, we'll be exploring an interesting coding problem. Problem number 2133, check if every row and column contains all numbers. In this challenge, we'll work with a matrix and dive into techniques to verify if every row and column contains all the required numbers. Let's get started. In this problem, we are working with an n×n integer matrix called grid. Each value in this matrix is within the range of 1, n. Our goal is to determine if every row and every column of the matrix contains all integers from 1 to n, inclusive. If this condition is satisfied, we return true, otherwise, we return false. The input to this problem is the grid, which is represented as a two-dimensional array, and it's guaranteed that each element in this array will be an integer within the valid range. The output is a Boolean value, true if the grid meets the criteria, or false if it does not. Let's look at some examples to better understand the requirements of the problem. Consider the first example where grid is a 3 by 3 matrix, 1, 2, 3, 3, 1, 2, 2, 3, 1. Each row in this matrix contains all the integers from 1 to n. For instance, row 1 has the numbers 1, 2, 3, row 2 has 3, 1, 2, and row 3 has 2, 3, 1. Similarly, each column also contains all numbers from 1 to n. Column 1 contains 1, 3, 2, column 2 contains 2, 1, 3, and column 3 contains 3, 2, 1. Since all rows and columns meet the condition, the output for this example is true. Now, let's look at another example where grid is 1, 1, 1, 1, 2, 3, 1, 2, 3. Here, row 1 only contains 1, which is missing integers 2 and 3. However, row 2 and row 3 do contain all integers from 1 to n. When we examine the columns, we see that column 1 contains 1, 1, 1, which is also missing integers 2 and 3. This causes the grid to fail the condition for columns. Based on this, we can already determine that the output will be false. Additionally, column 2 contains 1, 2, 2, which is missing the integer 3, and column 3 contains 1, 3, 3, which is missing the integer 2. These violations further confirm that the grid does not satisfy the problem's requirements. Since not all rows and columns contain every integer from 1 to n, the final output for this example is false. Now, let's consider a simpler example to solidify our understanding. If the grid is 1, it consists of a single row and column, both of which contain just the number 1. Since 1 is the only number in the range, 1, n, for this case, the output is true. Finally, let's go over the constraints and edge cases for this problem. First, the grid is always a square matrix, meaning the number of rows equals the number of columns. The size of the grid, n, can range from 1 to 100, and each element in the grid is guaranteed to be an integer between 1 and n. Key edge cases include the smallest possible grid, such as 1, which should always return true. Another edge case is when a row or column contains duplicate numbers, which will result in a false output since some integers are missing. For larger grids, like when n equals 100, we need to efficiently verify the condition for all rows and columns. Finally, grids with missing numbers in any row or column will also fail the condition. These constraints and edge cases are critical to consider when designing a solution for this problem. To solve this problem, we need to verify that every row and column in the given n×n matrix contains all integers from 1 to n. A straightforward solution is the brute force approach, where we manually iterate through each row and column, checking if the numbers 1 to n are present. We can use a set to store the numbers we encounter in each row and column and confirm whether the size of the set matches n. However, while this method is simple and easy to understand, it becomes inefficient for larger matrices. This inefficiency arises because we perform redundant checks for every row and column, leading to a time complexity of O(n) cubed. Additionally, the space requirement is O(n), due to the temporary sets used for each row and column. While it's simple to implement, this approach is not ideal for larger inputs due to its lack of scalability. To address these limitations, we explore an optimized approach using sets. The optimized approach utilizes pre-computed sets to improve efficiency. First, we create a target set containing all integers from 1 to n. This target set represents the required elements that each row and column must contain. Then, for each row, we convert its elements into a set and compare it to the target set. Similarly, for each column, we extract its elements into a set and perform the same comparison. If all rows and columns match the target set, we return true, otherwise, we return false. This method eliminates the need for redundant membership checks, as the set comparison is both quick and precise. The time complexity is reduced to O(n) squared, because we process each row and column once, and the space complexity remains O(n) due to the temporary sets. While this approach is slightly more memory intensive than brute force, it is far more efficient for larger matrices. Additionally, it's straightforward to understand and implement, making it a strong candidate for our chosen strategy. Another alternative is to use sorting instead of sets. In this approach, we sort each row and column and compare the sorted result to the sequence 1, 2, n. Sorting naturally handles duplicates and ensures that all integers are in the required range. The steps involve sorting each row and checking if it matches the expected sequence, then repeating the process for each column. While this method is simpler to implement in some languages, its major drawback is the higher time complexity. Sorting each row and column requires O(n) log n time, resulting in an overall complexity of O(n) squared asterisk log n. This makes it slower than the set-based approach for larger matrices. Additionally, it still requires O(n) space for temporary storage during the sort operation. While sorting can be an intuitive way to solve the problem, it is less efficient for larger inputs compared to the optimized set-based approach. After analyzing the different strategies, we chose the optimized approach using sets as the best solution for this problem. This method balances efficiency and simplicity, making it well suited to the problem's requirements. By pre-computing the target set and leveraging set operations, we avoid redundant checks and achieve an optimal time complexity of O(n) squared. Set operations such as creation and comparison are faster than sorting for this scenario, especially when working with larger matrices. Additionally, the clarity of set-based logic directly aligns with the problem's goal of verifying uniqueness and completeness in each row and column. Compared to brute force, this approach reduces the time complexity from O(n) cubed to O(n) squared, eliminating unnecessary operations. While sorting is another viable option, it introduces a logarithmic overhead, which makes it less efficient. The only trade-off is the slightly higher memory usage due to temporary sets, but this is negligible given the constraints, making the set-based approach the most scalable and practical choice. By leveraging sets, we create a solution that is both efficient and easy to understand. The use of pre-computed sets ensures that we meet the problem's requirements with minimal overhead, achieving a clean and effective implementation. This approach handles the input constraints gracefully, offering a robust solution that balances clarity, performance, and scalability. For these reasons, the optimized approach using sets is the ideal strategy for solving this problem. In this problem, we are tasked with determining whether every row and every column of a given nxn matrix contains all integers from 1 through n. To solve this, we can break the algorithm into clear steps. First, input validation is crucial. We need to confirm that the matrix is square, meaning it has an equal number of rows and columns. If this condition isn't met, we can immediately conclude the result is false. Next, we initialize our process by extracting the size of the matrix as n and defining a helper function called is_valid. This function will play a key role by checking if a given sequence, either a row or a column, contains all integers from 1 to n. It does this by converting the sequence into a set and comparing it to the target set, 1, 2, n. We also initialize a variable result to true to store our final outcome. With these preparations in place, we can start evaluating the rows of the matrix. For each row, we pass it to the is_valid function. If the function finds that a row is invalid, we update result to false and terminate the row checking process early. After evaluating all rows, we turn our attention to the columns. To check a column, we extract its values using list comprehension. This allows us to dynamically generate the sequence of elements in the column. Once we have a column, we pass it to the is_valid function, just as we did with the rows. If the function determines the column is invalid, we set result to false and stop further checks. Finally, after processing both rows and columns, we return the value of result. This summarizes whether the matrix satisfies the condition that each row and column contains all integers from 1 to n. Now, let's discuss some key insights. Using a set for validation is particularly efficient because it eliminates duplicates and allows for fast membership checks. Comparing the set of a sequence to the target set, 1, 2, n, ensures that all required elements are present and that no duplicates exist. Additionally, this approach is computationally efficient. Iterating through rows and columns takes n squared time, and the set comparison for each row or column is n, resulting in an overall time complexity of n squared. We should also consider edge cases when implementing this algorithm. For instance, if the input matrix is not square, such as 1, 2, 3, 4, 5, we should return false immediately. Similarly, if any row or column has missing or duplicate elements, the validation will fail, as the set comparison will not hold. For the smallest possible matrix, such as a 1x1 grid with the value 1, the algorithm should correctly return true. To implement this, we rely on a few data structures. The set data structure is critical for validating the presence of all integers from 1 to n, as it offers constant time operations for adding elements and checking membership. Additionally, list comprehension is used to extract columns from the grid dynamically. This is a concise and efficient method for generating column sequences that we can then pass to the validation function. With these tools in place, we can construct the algorithm. Now, let's look at the Python implementation. First, we begin by checking if the input grid is square. This is done by comparing the number of rows and the lengths of each row. If any row length differs from the number of rows, we return false right away. The next step is defining the helper function is_valid. This function determines whether a sequence contains all integers from 1 to n by converting the sequence into a set and comparing it to the target set generated using range 1, n plus 1. With this function in place, we then proceed to validate all rows. For each row in the grid, we call is_valid. If any row fails the validation, we return false immediately. The process for columns is similar. For each column, we use list comprehension to dynamically extract the column values and pass the resulting sequence to is_valid. Again, if any column fails validation, we return false. If all rows and columns pass the checks, the function returns true. This implementation is straightforward, leveraging the helper function to keep the validation logic modular and reusable. It also ensures clarity by separating the row and column checks into distinct steps. To further optimize the algorithm, we can introduce a couple of enhancements. First, we can implement an early exit mechanism. If any row or column fails validation, we can stop processing immediately, avoiding unnecessary computations. This ensures the algorithm terminates as soon as it detects an invalid row or column. Second, instead of generating the target set 1, 2, n repeatedly within the is_valid function, we can pre-compute it once and reuse it throughout the validation process. This reduces redundant operations and improves efficiency. Analyzing the complexity, we see that the time complexity remains n squared, as we must check all rows and columns, with each validation taking n time. The space complexity is n, as we need to store the target set in temporary column sequences. This balance of simplicity and efficiency makes the algorithm robust for matrix validation tasks, ensuring correctness while minimizing computational overhead. This solution verifies whether every row and column of the given grid contains all integers from 1 to n. Let's break it down. 1. Extract the grid size. The variable n is set to the length of the grid, representing the number of rows and columns since the grid is square. 2. Define target set. The target_set is defined as the set of integers from 1 to n. This set represents the expected values that each row and column must contain. 3. Validate rows. The code iterates over each row and grid and checks if the set of elements in the row matches target_set. If any row fails this check, the function immediately returns false. 4. Validate columns. For each column index, a set is created from the values at that column across all rows. This set is then compared to target_set. If any column fails this check, the function returns false. 5. Return true. If all rows and columns pass the checks, the function returns true. The solution is efficient, with time complexity n squared, due to the nested loops for row and column validations, and it leverages Python sets for quick membership checks. This ensures correctness and handles edge cases like grids with missing or duplicate numbers effectively. Here, we start by importing the necessary libraries and defining our solution class. The main method checkValid takes a two-dimensional grid as input, where we need to verify if every row and column contains all numbers from 1 to n exactly once. First, we determine the size of the grid, n, and create a target set that holds all integers from 1 through n. This target set will be used as a reference for comparison. Next, we focus on validating all the rows. For each row in the grid, we initialize a new set to collect the unique numbers in that row. As we iterate through the elements of the row, each number is added to the set. Once the row's numbers are collected, we check if the set of numbers in the row matches the target set. If it doesn't, this means the row is invalid, and we return false immediately. This ensures we don't waste time checking further rows if one is already incorrect. After validating all the rows, we move on to checking the columns. For every column index from 0 to n1, we initialize a new set to capture the unique numbers in that column. By iterating through each row of the grid, we extract the element at the current column index and add it to the set. Once all elements of the column have been processed, we compare the column set to the target set. If the two sets are not equal, it means the column does not contain all numbers from 1 to n, and we return false. If no mismatches are found across both rows and columns, the method concludes by returning true, indicating that the grid satisfies the required condition. Here, we have a grid of size 3 by 3 as the input. The goal is to check whether every row and column contains all numbers from 1 to 3. First, we initialize two key variables, n, which is the size of the grid, and target_set, which holds the set of expected numbers, 1, 2, 3. Next, we start validating all rows. For the first row, we convert its elements into a set, resulting in 1, 2, 3, which matches target_set. This means the first row is valid, so we proceed to the second row. Similarly, the set of the second row is 3, 1, 2, which also matches target_set. Finally, we check the third row, and its set, 2, 3, 1, is again valid. Since all rows meet the requirement, we move on to verifying the columns. Now, we check all columns in the grid. For the first column, we extract the values 1, 3, and 2 from the grid, convert them into a set, and get 1, 3, 2, which matches target_set. So, the first column is valid. Next, we analyze the second column, which contains the values 2, 1, and 3. Converting this to a set results in 2, 1, 3, which also matches the expected numbers. Lastly, for the third column, the values are 3, 2, and 1, giving us the set 3, 2, 1, which is valid as well. Since all rows and columns are correct, the grid satisfies the conditions, and we return true. This concludes the first example, which demonstrates a valid grid. In the second example, the grid contains a problem in one of the rows. Again, we start by initializing n as 3 and target_set as 1, 2, 3. Moving to the row validations, the first row forms the set 1, 2, 3, which is valid. The second row forms the set 3, 1, 2, which is also valid. However, the third row results in the set 2, 2, 1. Here, the number 3 is missing, and there's a duplicate value instead. This makes the row invalid. Since we've already identified an issue, there's no need to check the columns. The function immediately returns false, as the grid fails the validation due to the problematic row. In this third example, the grid has issues in both a row and a column. We begin by initializing n as 3 and target_set as 1, 2, 3. First, we validate all rows. The first row forms the set 1, 2, 3, which is correct. The second row forms 3, 1, 2, which is also correct. However, the third row produces the set 2, 1, 1. This is invalid because the number 3 is missing, and there's a duplicate value. Even though we've identified a row issue, let's check the columns for completeness. The first column results in the set 1, 3, 2, which is valid. The second column gives 2, 1, 3, which is also valid. Finally, the third column produces 3, 2, 1, which is invalid, as the number 2 is missing. With both row and column issues present, the function returns false because the grid does not meet the criteria. This approach works by ensuring that every row and column contains exactly the numbers from 1 to n. The target underscore set provides the expected values, and we validate rows and columns independently by converting them into sets. If any row or column fails the check, the function terminates early and returns false. The use of sets is highly efficient here, as it simplifies validation by inherently handling duplicates and ignoring the order of elements. In terms of complexity, the solution operates in O, in superscript 2, time due to the need to iterate through all rows and columns in the grid. The space complexity is O, n, which accounts for the target underscore set and temporary sets created during validation. Overall, this method is both efficient and straightforward, ensuring that grids are validated quickly while handling invalid cases appropriately. The time complexity of our solution is determined by two main tasks: checking all rows and checking all columns. Let's first analyze the row checks. For each of the n rows in the grid, we convert the row into a set and compare it with the target underscore set. Converting a row to a set involves iterating through n elements, which is an O, n, operation. Since we perform this for all n rows, the total time complexity for row checks becomes n asterisk O, n, or O, n squared. Similarly, for column checks, we construct a set of elements for each of the n columns by iterating through all n rows. Constructing a set for one column is an O, n, operation, and within columns, this also results in a time complexity of n asterisk O, n, or O, n squared. When we combine the time complexity for both row and column checks, the total becomes O, n squared, plus O, n squared, or simply O, n squared. Now considering space complexity, we start with the target underscore set, which contains integers from 1 to n. This requires O, n, space. Next, for each row, we create a set of its elements. At any given time, the memory usage for this set is O, n, and since we process rows sequentially, the space is reused, keeping the contribution at O, n. Similarly, for columns, constructing a set of n elements also requires O, n, space at a time, and as with rows, this space is reused for each column. Therefore, the space required for column sets remains O, n. Adding these components together, the overall space complexity is O, n, from the target underscore set plus O, n, from the row and column sets, resulting in a total space complexity of O, n. When comparing this solution to a brute force approach, the difference becomes clear. A naive approach might involve explicitly iterating through each row and column multiple times to count occurrences of integers from 1 to n. This would significantly increase the time complexity to O, n cubed, as each element might be revisited multiple times across all rows and columns. In contrast, the given solution optimizes this process by leveraging sets, which allow efficient membership checks. By processing each row and column in linear time relative to its size, the time complexity is reduced to O, n squared. Moreover, the reuse of memory for row and column sets ensures that space usage is minimized, maintaining an efficient O, n, space complexity. Analyzing the best, average, and worst cases provides further insight into the algorithm's behavior. In the best-case scenario, if the first row or column fails the check, the algorithm can exit early, reducing the time complexity to O, n. For the average case, the algorithm typically processes several rows and columns before finding an invalid one, leading to a complexity closer to O, n squared. In the worst case, when all rows and columns pass the checks, the algorithm processes the entire grid, resulting in a time complexity of O, n squared. Mathematically, for n rows and columns, each set operation, creation and comparison, scales linearly with the size n. Since there are n rows and n columns, the total number of operations scales quadratically, confirming the overall time complexity of O, n squared. Meanwhile, the space usage is dominated by the target underscore set and temporary row and column sets, which scale linearly with n, leading to a space complexity of O, n. When solving this problem, there are several common mistakes to watch out for. First, it's important to validate that each row and column contains exactly the integers from 1 to n, no duplicates, no missing values. For example, a row like 1, 2, 2, 4 might seem unique but fails the requirement because the number 3 is missing, and there's a duplicate too. Another frequent mistake is neglecting edge cases, such as when the matrix is empty or has only one element. These scenarios can lead to unexpected errors if not handled properly. Additionally, some solutions only check rows or only check columns, but both must be validated independently. Finally, inefficient use of data structures, such as recalculating unique numbers repeatedly without leveraging sets or dictionaries, can make your solution slower than necessary. These inefficiencies are especially noticeable in larger matrices, so it's critical to choose the right approach for both correctness and performance. Matrix size is another key consideration. When working with very large matrices, such as 10,000 by 10,000, brute force methods often lead to timeouts because of their high computational cost. Optimizing for time complexity is essential to ensure your solution scales. Now, let's discuss insights that can help you excel in interviews. First, break the problem into two clear parts: validation and traversal. Cleanly separating logic for rows and columns makes the solution more structured. Using hash sets for validation is particularly efficient, as they provide constant time operations for checking duplicates and missing numbers. To further optimize, you can validate rows and columns simultaneously, reducing the number of passes through the matrix. Be prepared to handle edge cases, like matrices of size 0 or 1, or even invalid entries outside the expected range of 1 to n. Finally, interviewers often evaluate your ability to explain trade-offs. Clearly articulating the differences between brute force and optimized methods demonstrates your understanding of computational efficiency and problem-solving strategy. This problem shares similarities with other matrix-related challenges, and practicing these can strengthen your problem-solving skills. For example, LeetCode 36, Valid Sudoku, involves grid validation but adds the twist of checking 3 by 3 subgrids. LeetCode 73, Set Matrix Zeros, requires manipulating rows and columns based on specific conditions, which helps build an understanding of how to efficiently traverse and modify matrices. LeetCode 54, Spiral Matrix, involves traversing a 2D matrix in a spiral pattern, which is another exercise in structured traversal logic. Lastly, LeetCode 566, Reshape the Matrix, focuses on transforming a matrix into a new shape while handling edge cases, such as mismatched dimensions. These related problems provide a great opportunity to refine the skills needed for this challenge, like efficient traversal, validation, and handling edge cases. There are multiple approaches to solving this problem, each with its own trade-offs. A brute force approach involves iteratively checking each row and column to ensure they contain all integers from 1 to n. While this method is straightforward, it has a time complexity of n cubed, due to nested loops and repeated validations, making it inefficient for large matrices. A more efficient method uses hash sets to validate rows and columns. By leveraging the constant time operations of hash sets, you can reduce the overall complexity to n squared. This approach avoids redundant checks and is significantly faster for larger inputs, though it requires slightly more careful implementation. For advanced optimization, bit masking can be used to represent the presence of integers in rows and columns with bitwise operations. This also achieves n squared complexity, but it reduces memory overhead and is particularly useful when memory is constrained. However, bit masking requires a deeper understanding of bitwise logic and can be harder to debug, so it's less intuitive for most developers. Each of these approaches has its strengths, and the best choice depends on the constraints and requirements of the problem at hand. Great job! To wrap up, we reviewed the problem, discussed the brute force approach, and highlighted key insights. Remember, matrix traversal and hash-based techniques are essential skills for grid problems. Thanks for watching, and don't forget to like and subscribe for more content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!